The Milky Way is a band of fire fueled by the vapors of Earth.
The world is made of earth, water, fire, and ether.
The sun is the brightest star in the cosmos.
The earth is the center of the universe.
Throughout the course of human history, we have wondered about what the universe is and where we fit into it. Our ideas about the cosmos, both mythic and scientific, have continuously changed. No sooner do we get comfortable with one theory and then another pops up. Even today, some of the most advanced measurements of space have a 30% margin of error. It may be that our current perceptions will be as quaint in the future as the beliefs of the past seem to us now. One thing seems inevitable. We will always be on a quest to unlock the mysteries of the cosmos. Aristotle's belief that stars are fixed in unchanging space held a firm grip on Western thinking well into the 20th century. Even Albert Einstein didn't question it and assumed that the universe doesn't change in time. In 1929, that ancient assumption was finally challenged by the American astronomer Edwin Hubble. Peering through a telescope on Mount Wilson in California, he focused on this fuzzy patch in the constellation Andromeda. Hubble observed stars so far away that he realized he was looking at another galaxy more than 2 million light years away. As he looked deeper into space, he found more galaxies and noticed that they were moving apart. The farther away they were, the faster they appeared to recede. The evidence was in their light. Just like the pitch of sound changes when an object approaches or retreats, light shifts to the blue end of the spectrum when it is moving towards us and towards the red end when it is moving away. Because the space between the galaxies was stretching, the wavelengths of their light were getting redder. Hubble's discovery implied that there was a starting point, a moment when time and space began, the Big Bang. Wherever and however the Big Bang took place, the theory insists that in the biggest explosion of all time, a speck smaller than an atom gave rise to all matter. Subatomic particles were drawn into clumps by gravity, and simple atoms like helium and hydrogen were formed. Balls of hydrogen grew bigger and hotter as their gravity increased. Stars were born, stars that shine and explode and seed the universe with the elements of life. Attracted by gravity, stars collected in galaxies. Hubble thought the shape of galaxies indicated their age, that they began as formless clusters that wound tighter and tighter over time, and that arms grew and wrapped up the galaxy like a ball of string. On this point, Hubble was wrong. Different galaxies have different shapes, whatever their age. Among the millions of spiral galaxies is the one we call home, the Milky Way. Our galaxy is a huge disk of 200 billion stars, so big that for light to travel from one side to the other takes 100,000 years. We're located in a blue arm of the galaxy, 2/3 of the way out from the center. Out here, young stars appear blue. In the orange glow of the hub are older stars, billions of them. Clusters of ancient stars over 12 billion years old hover outside the disk. On Earth, the best view of the Milky Way is from the southern hemisphere in winter. As the Earth turns over the course of a night, the bright center of the galaxy can be seen moving into frame. A wispy stellar arm extends to the right. It's out of these galactic suburbs where we find nebulas, clouds of dust and gas that give birth to stars. Gravity makes clumps of matter in the nebula collect. The clump grows more dense and its gravity increases. When it's squeezed tight enough, temperatures soar, nuclear fusion sparks, and a star is born. Hydrogen makes up most of a star. In a continuous nuclear reaction, the star converts hydrogen into helium. All that prevents the star from exploding into space is the opposing pull of its gravity. Smaller stars burn cool, red, and dim. More massive stars burn blue and bright. Small red stars may endure for 100 billion years or more, but big blue stars burn out quickly, lasting only a few billion years. The fate of a star depends on how massive it is. The smallest of stars simply burn out and fade away, but most end their lives more dramatically. When a star uses up its hydrogen fuel, it grows red and swells up. Eventually, the core collapses and the star explodes. The bigger the star, the bigger the bang. The outer layers of the star blow off, leaving behind a ring-shaped nebula. With an average-sized star like our Sun, the remaining core becomes a white dwarf, a star without nuclear energy about the size of Earth. Supergiants, 10 to 50 times the size of our Sun, live fast and die young. A star 10 times the mass of the Sun burns fuel 5,000 times more quickly. When they end in powerful supernova explosions, they leave behind tiny, extremely dense neutron stars. Just 1 teaspoon of a neutron star weighs as much as the Empire State Building. Also called pulsars, they have as many as 500,000 Earth masses packed into a body about the size of New York City. Their magnetic fields are so intense that energy emitted from the star gets caught and spun into narrow beams at the poles. It's only when the poles spin in our direction that we see a flash of light. biggest of supergiants go a step further. When they go supernova, they leave behind mysterious points of nothingness, black holes. The density of a black hole is so great that even light cannot escape its gravity. Supernova blasts are thought to lead to the creation of new stars. In the wake of their explosions, matter is left swirling around in nebulas. Gravity forces it to collect, eventually forming new stars and planet systems like our own. Supernovas seed the galaxy. In the Chilean Andes in 1987, for the first time since the invention of the telescope, astronomers found a supernova. Their view of the southern skies included two wispy patches of light, the Magellanic Clouds. Their companion galaxies, 170,000 light-years away. With a pop like a cosmic flashbulb, previously faint stars suddenly became one of the brightest points in the sky. The Anglo-Australian Observatory in New South Wales had one of the best vantage points on Earth. The Australians captured this extraordinary image of the very blast of the supernova. The shock waves of an exploding star like the Magellanic supernova may have triggered the birth of the Sun. About 5 billion years ago, a whirling cloud of gas and dust became increasingly concentrated. As the cloud condensed, its gravity increased. The center became intensely hot, and nuclear reactions began in our Sun. The Sun is the driving force behind every living thing on our planet. Without its energy, life would never have emerged on Earth. Every day, the Sun rises at a slightly different place, moving eastward over the course of a year. 2 days a year, midsummer and midwinter, the sunrise doesn't move. This burial site in Ireland is a Stone Age marker of the winter solstice. It was built so that on December 21st, the shortest day of the year, the sun lights up the chamber of the tomb inside. It hasn't failed for 5,000 years. It is just one of many structures throughout the world that mark the positions of the sun, moon, stars, and planets. 3,500 years ago, the Egyptians revered the sun as a god by the name of Ra. Their mix of myth and astronomy is epitomized at Abu Simbel. They believed that Ra was reborn every time the first rays of sunrise enter the temple's great hall. The sun was once thought to be a perfect shining ball, but since the invention of the telescope, astronomers could see that it is constantly changing. Dark spots come and go, and huge flares of gas leap from its surface. In X-ray, it's alive with brilliant explosions, a cauldron of energy. Our sun is an average-sized star, about 1 million times the size of Earth. It takes a month to rotate on its axis and is located 93 million miles away from us, just the right distance for life to flourish here on Earth. From surface to core, the Sun is almost 500,000 miles. There's a big difference in temperature from 27 million degrees at the core to 10,000 on the surface. What makes this solar colossus so hot is nuclear fusion. Fusion is caused by enormous pressure. In the core, hydrogen atoms collide with such a force that they fuse and make helium. The center of the Sun is like a continuous hydrogen bomb. Because the matter in the Sun's core is so dense, it takes a long time for energy to make its way to the surface, about 1,000,000 years. Slowly, energy moves outward, first by radiation, then in huge convection waves, like soup bubbling on a stove. Each yellow bubble is the size of Texas. To learn more of our local star, a robot spacecraft named Ulysses set out on a 5-year solar polar mission. It was sent far below the orbital plane of the planets for a unique vantage point. By late 1994, for the first time ever, the probe was peering at the south pole of the Sun. Ulysses sensed what astronomers could not. Magnetic force lines, here in blue, swirling and tangling as the Sun rotates. When force lines pass through the surface of the Sun, they pinch and slow the gases in their paths. This creates sunspots, places where it's 3,000 degrees cooler than the surrounding ocean of yellow heat. Sunspots like this one are big enough to swallow the Earth. Magnetic force also causes the shaggy edges of the spots, like iron filings sprinkled near a magnet. Sunspots usually come in pairs at the departure and re-entry points of a force line. These great arcs, called prominences, are bent around force lines. Like horseshoe magnets, searing gas traces out the magnetic loops. Even more spectacular are flares, eruptions with the energy of 10 million hydrogen bombs. Flares eject stupendous amounts of material at millions of miles an hour. Energized particles are hurled outward and are a major source of the solar wind. Like a garden sprinkler, the Sun sprays the solar wind toward the planets. The electrically charged particles reach the Earth in a day or so, but are largely deflected. The metal in the Earth's core behaves like a huge magnet, repelling most of the particles, but pulling some in at the poles. The particles spiral downward, forming 2 oval crowns at the north and south poles. When they react with the Earth's upper atmosphere, they put on spectacular light shows, the aurorae. The Sun is also responsible for weather on Earth. Air warmed by the Sun rises at the equator and heads towards the poles. In the mid-latitudes, it runs into cool air headed the other way. Storms are caused by these streams bumping into each other. The planets are all held in orbit by the gravitational force of the Sun. But the Sun was not always believed to be the center of the solar system. In the 4th century BC, Aristotle put forth a theory that the natural place of Earth was at the center of the universe. The Earth was motionless, and revolving around it were the sun, planets, and stars, attached to rigid spheres. But there was a problem with Aristotle's theory. The planets were a puzzle. Because their progress through the heavens could be erratic, they were called wandering stars. Five centuries later, the Greek astronomer Ptolemy decided the drift was due to epicycles, little orbits the planets made around their main orbital paths. Ptolemy's theory worked for planets like Mercury and Venus, which speed across the sky at twilight, but failed for others, like Mars. For over 1,000 years, not much progress was made until 1543, when the Polish astronomer Nikolai Copernicus abolished the notion of an Earth-centered cosmos. At the cost of rejecting the intuitive feeling that the Earth is at rest, he put the Earth in motion, rotating on its axis and orbiting the Sun. But his belief that the orbits of the planets were perfect circles left the eccentric loops of Mars unexplained. Arguments ensued for the next half-century, as neither the theories of Ptolemy or Copernicus could be proved. The observation that proved that the Earth and planets orbit the Sun were made by the Danish astronomer Tycho Brahe, who ironically refuted the Copernican model. He believed that the planets revolved around the Sun, but that the Sun orbited the Earth. To prove his theory, Brahe spent 20 years making meticulous observations of the movements of the planets. After he died in 1601, Brahe's observations were used by a German mathematician named Johann Kepler to prove that all of the planets orbit the Sun. By 1609, he had worked out that the orbits of the planets aren't circles, but ellipses, and that the speed of the planets depends on their distance from the Sun. Enter the English scientist Isaac Newton, who explained more about orbits with his famous theory of gravity. Newton's genius was to recognize that the force that makes an object fall to Earth is the same force that governs the motions of moons and planets. The shape and speed of an orbit depends on the strength of the gravitational force, and gravitational force depends on size and distance. The closer and more massive the objects, the greater the pull. So the closer a planet is to the Sun, the faster it moves. Naturally, Mercury has the shortest year of all the planets. It makes its way around the Sun more than 4 times in one Earth year. Mercury is a barren world, scorched, airless, and heavily cratered. Like a magnet, the Sun's powerful gravity attracts debris from space. With Mercury in the line of fire, the planet takes a lot of hits. Its proximity to the Sun also makes it hot enough to melt lead. By day, temperatures exceed 800 degrees, but it's not the hottest planet. At 900 degrees, that honor falls on Venus. Shrouded by clouds of sulfuric acid, Venus suffers the ultimate runaway greenhouse effect. With an atmosphere heavy with carbon dioxide, the Sun's heat is trapped. Until recently, the clouds of Venus concealed its nature. To this day, these are the only pictures of its surface. They were radioed to Earth before the landing craft melted. Radar mappers painted a better picture. They electronically pierced the clouds to give the first wide-angle images of Venus, a smoother planet than expected. There are fewer craters and less contour than on Earth or Mars. These pancakes are volcanic eruptions flattened by the atmosphere. Pressure here is 90 times greater than on Earth. Of all the planets, Venus has the most volcanoes, this one a mile high and probably extinct. Neither Mercury or Venus have moons. The intense gravity of the sun would pull them away from the planets. Earth's satellite is the first in the solar system. It would fit comfortably across North America, making it average size for a moon. The moon always presents the same face to Earth. We never see the other side. The reason is that the moon's orbit and rotation are exactly the same. It takes 27 days to spin on its axis and 27 days to make its way around Earth. In 1992, a Jupiter-bound spacecraft called Galileo sailed by the moon. As it did, Galileo gave us a new perspective. For the first time, we saw the Earth and Moon moving together in space. Two of the tiniest moons of the solar system orbit our neighbor, the red planet Mars. The Martian satellites may be captured asteroids. They're smaller than 15 miles across. Next to Earth, Mars is the most likely incubator of life. We know it once had water. There are polar ice caps to prove it. Photographs from space probes show other evidence of water, like this network of channels. Volcanic peaks point to an exciting past. This one, Olympus Mons, is over 15 miles high. It's the tallest mountain in the solar system, nearly 3 times the size of Mount Everest and big enough to cover the state of Colorado. Mars is cold and dry. It averages below zero temperatures and is so arid that it experiences tremendous dust storms, big enough to envelop the entire planet. This is the mother of all storms, a great red spot over twice the size of Earth. It's been raging for at least 350 years. Jupiter seethes with weather. One reason for Jupiter's turbulent weather is the speed of the planet's rotation. Its day is less than 10 hours. Like pizza dough being spun in the air to make it stretch, Jupiter rotates so fast that it expands at the equator. Cloud bands at the equator move slower than those near the poles. Where these bands meet, storms begin. Jupiter is more massive than all the other planets combined. If the Earth was the size of a pea, Jupiter would be an orange. It's big enough to house all the planets and moons of the solar system. One of the first people to study the sky through a telescope discovered that Jupiter has moons. In 1610, Galileo found 4 of the 16 moons orbiting the giant planet. These Galilean moons are bigger than Pluto. Three and a half centuries later, we sent probes to study the outer planets. Voyagers 1 and 2 launched in 1977. It took Voyager 2 years to reach Jupiter, where it uncovered its ring, too narrow to be seen from Earth. From Jupiter, the Sun is little more than a star, 500 million miles away. It's another 300 million miles to Saturn, Lord of the Rings. In the early 80s, Voyager ended centuries of speculation. Until then, astronomers thought that Saturn had just 6 or 7 rings. It turned out that there are hundreds of rings orbiting in 7 main bands. Made mostly of hydrogen gas, Saturn is the least dense of all the planets, even less dense than water. Given a big enough swimming pool, it would float. Voyager also visited Uranus, 900 million miles past Saturn and almost 2 billion miles from the Sun. Uranus has an unusual tilt. Its axis is almost aligned with its orbital plane. Some astronomers suggest that Uranus was once dealt a blow fierce enough to knock the giant planet 98 degrees off kilter. Uranus has 15 moons. The most unusual is Miranda, which seems to have been blasted apart by a huge impact, then put back together. It's riddled with cliffs, craters, and canyons, some 10 times deeper than the Grand Canyon. These ice cliffs are 12 miles high. If you jump from them, you wouldn't hit bottom for over 12 minutes, thanks to minimal gravity. Another unusual moon feature is on Triton, one of the 8 moons of Neptune. It is the coldest body in the solar system. Despite a chilling temperature of minus 390 degrees, it is volcanically active. At its south pole is a geyser that spurts dust plumes 5 miles high. It makes geysers on Earth seem like water fountains. Neptune is another planet with killer storms. Like the Wizard's Eye. Just above is a great dark spot, a tempest the size of Earth. Around it, gales have been known to blow at 1,200 miles per hour, the fastest in the solar system. The most elusive planet is tiny Pluto. At more than 3.5 billion miles from the Sun, we didn't even know it existed until 1930. In 1990, the Hubble Space Telescope captured the best images to date of the planet and its moon Charon. Strictly speaking, Charon doesn't orbit Pluto. They're both in orbit around their common center of gravity. Some astronomers consider them a double planet. Occasionally, our solar system is visited by comets. From Earth, they can grace the heavens for weeks at a time. Egyptians believed they were messages from the gods, but comets are really just leftovers from the formation of our solar system. When the planets were formed, bits and pieces of rock and ice ended up outside the orbital plane. This formed a large shell of debris known as the Oort cloud. It's from Oort that comets fall. The nucleus of a comet is a clump of dirty ice, ranging in size from a football stadium to an entire city. During its multi-billion-mile odyssey, a comet may sprout a tail. Once a comet is inside the orbit of Jupiter, ice is vaporized by the heat of the sun. The dust and gas of a comet's tail can stretch as far as 100 million miles, more than the distance from the Earth to the sun. Some comets travel on random elliptical orbits among the planets. Kamikaze comets plunge directly into the sun. Others just graze its fiery surface. Long ago, a comet swung close by Jupiter and had its orbit changed by the gravity of the giant planet. That comet was Halley. Thanks to Jupiter, Halley is locked into a 76-year cycle, following a path that takes it around the Sun and out beyond Neptune. The 17th century astronomer Edmund Halley led us to our first understanding of comets. Until his time, scientists thought they were just one-time visitors to our skies. They simply careened past Earth, never to return. But in 1680, Halley's friend Isaac Newton carefully observed the motion of a comet and figured out that it was traveling in a closed orbit. Newton suggested that a comet with a small enough orbit might be seen again and again. To test the idea, Edmund Halley analyzed the sightings of 24 comets. It turned out that 3 of them were separated by the same 76-year interval and seemed to have virtually identical orbits. If he was right, the comet would show up again in 1758. Long after Halley's death, the comet appeared on schedule. Astronomers then traced it back through time. One of these Chinese tomb drawings confirms the appearance of Halley's comet in the 2nd century BC. Halley was also seen in Julius Caesar's time. A coin struck in his memory bears its image. In 1301, the Italian painter Giotto made Halley's comet the Star of Bethlehem. When Halley appeared in 1910, history's most famous comet was in vogue. For the first time, Halley's comet was photographed. 76 years later, Halley was greeted with super-sensitive cameras and giant telescopes. Scientists did more than merely observe the comet in 1986. As Halley sped past, 5 robot spacecraft raced to intercept it. 2 Soviet, 2 Japanese, and a European probe called Giotto, after the Italian painter. As Giotto approached, computer images allowed scientists unprecedented insight into the comet's brightness and density. But the pictures disappointed television viewers. Supercomputers later produced the view the public had expected. At the center, a peanut-shaped nucleus, a lump of primeval matter 6 miles by 9. Geysers of gas streamed at 20 tons a second. Through the fog, this was the very face of Halley. When comets take a trip through the solar system, they leave behind trails of dust. When the Earth encounters the wake of a comet, tiny grains hit our atmosphere at up to 40 miles per second. Friction causes them to burn up harmlessly in the upper atmosphere. We see them as meteors, shooting stars. When larger pieces of asteroids and comets hit our atmosphere, they usually burn up. If they're big enough and survive to hit the ground, they're called meteorites. Just by chance, a man with a video camera caught this fireball breaking up over Pittsburgh in 1992. Evidence of impacts on Earth can be difficult to spot. Over thousands of years, wind, weather, and vegetation disguise them. In Australia's dry climate, Gosses Bluff has survived over 20 million years. This crater is a whopping 9 miles wide. Meteor Crater in Arizona is considered the best Earth specimen. Its youthful age of not more than 50,000 years hasn't lent enough time to erosion. There are better places to observe the evidence of impacts. Preserved in the vacuum of space, moons are scarred with craters frozen in time. Some collisions can be truly catastrophic. On Saturn's moon Mimas is a crater 1/3 of the width of its body. The satellite was nearly destroyed by the impact. The Earth may have already experienced a similar catastrophe. At the tip of Mexico's Yucatan Peninsula, the space shuttle has turned up radar images of part of a crater dating back 65 million years. Theory suggests that an asteroid 5 miles wide plunged to the ground. Many scientists believe it devastated life on Earth and ended forever the rule of the dinosaurs. In 1993, we had our first opportunity to study a comet in action. Through this telescope at Mount Palomar, California, 3 astronomers, Eugene and Carolyn Shoemaker and David Levy, found a strange new comet. The streak of light in orbit around Jupiter was dubbed SL9. It was not a single comet, but a whole squadron of comets flying in formation, each with a dusty tail. From its perch in Earth orbit, the Hubble Space Telescope took this brilliant portrait of the SL9 fragments. They were formed in 1992 when the comet strayed too close to Jupiter. The planet's immense gravitational forces had torn the comet apart. 2 years later, the fragments would return to slam directly into the far side of Jupiter at 130,000 miles per hour. In July 1994, the Anglo-Australian Telescope in New South Wales kept watch. Day after day, as the string of mountain-sized fragments hit Jupiter, their points of impact came into view. Heat-sensitive images recorded over 20 major collisions. Hawaii's Keck telescope captured the impact of one of the biggest fragments. A mushroom cloud 600 miles high rose above Jupiter's horizon. For giant Jupiter, the impacts were pinpricks. Earth would not fare so well. The dark crescent in this picture is a shock wave as large as the Earth itself. On our planet, the collisions of the Shoemaker-Levy comet would have been catastrophic. Earth is a glittering jewel. There is no other place that can nurture such an extraordinary diversity of life, at least as far as we know. Looking for signs of life is like looking for a needle in a haystack. From space, it's even hard to tell that there is life on Earth. The only hint is the presence of oxygen. But at night, with the right sensors, the presence of humans is more obvious. We have learned to harness the energy of the sun to lengthen our days with artificial light. Slowly but surely, we have learned about Earth and where it fits in the cosmos. It all began with learning how to measure space. Over 2,000 years ago in Egypt, it was noted that at noon, the sun shone directly down a well in Aswan. At the same time in Alexandria, 500 miles to the north, a column cast a shadow. A Greek mapmaker by the name of Eratosthenes realized the difference was due to the curve of the Earth's surface. When the sun was directly overhead in Aswan, it was at an angle in Alexandria. The angles differed by 1/50th of a circle. Eratosthenes reasoned that the distance between Aswan and Alexandria must also be 1/50th of the circumference of the Earth. He was right. The Earth's circumference is about 25,000 miles. This gave the world the first unit of astronomical measurement, a unit the size of Earth. Astronomers could then use two distant points on the Earth's surface and some trigonometry to figure out how far the Moon is, 30 Earths away. The same formula was applied to each end of an orbit to measure bigger distances. By the time Edwin Hubble came on the scene in the early 20th century, sophisticated measurements of distant stars had been worked out, paving the way for his brilliant observations of galaxies. The technology of the last century has yielded more information about the universe than any other time in history. We now study not only light, but radio waves, infrared, X-rays, and ultraviolet. We use observatories on Earth and in space. It seems every time we turn around, something new is discovered. Possible life on Mars, ice caps on the Moon, black holes at the centers of millions of galaxies. At the Schmidt Telescope in Australia, scientists work to map the universe in 3D. Using a photograph of a distant region of the cosmos, they take new pictures of each galaxy within the photo, analyzing them for age and distance. All the information is processed on a computer and displayed as a segment of the universe, one piece of the cosmic jigsaw puzzle. Piece by piece, an overall picture is emerging. Strands of matter are strewn through unimaginable emptiness. Like dewdrops on a spider's web, each point of light is a cluster of thousands of galaxies. Although we now know what the universe looks like, we don't know how it got that way. Some of the most stunning data on the cosmos is coming back from our eyes in the sky, the Hubble Space Telescope. Outside the light pollution from cities and the distortion lens of Earth's atmosphere, Hubble is bringing home pictures of unmatched clarity. One recent image has had a profound impact on our notions of the size of the universe. the Hubble Deep Field. Aimed at a tiny dark patch of sky about the size of a pinhead held at arm's length, the scope took 342 repeated exposures. With each exposure, dimmer and dimmer objects came into view. Aside from a few stars, each point of light is an entire galaxy. Prior to seeing the Hubble Deep Field, astronomers thought there were at least 10 billion galaxies. Now they believe there are at least 50 billion. As with all discoveries, along with new answers come new questions. Would a longer exposure reveal even more galaxies? Do all tiny patches of the sky have as many? How big are all of these galaxies and how far away are they? As we peer further and further into space, we're sure to keep asking and reshaping our ever-evolving concepts of the universe.